function going to be transposed across y equals x?
So we are reflected across y equals x, causing the inputs and outputs to transpose. But what data are we looking for? What is Chandler asking about? What are we talking about when we say that we're reflecting across y equals x, that we're looking at those inputs and outputs transposed? Oh my gosh, guys, this is what we did all last week after the test. It's like what the Frere model it says on there, which means that we need to have our Frere models out like I asked. Our proficiency scales out. It's at the top of the proficiency scales. When we reflect across y equals x, when we transpose those inputs and outputs, what kind of function are we talking about? Someone said radical, that's only for power functions. They are going to be logarithms. Inverse function. Woo! Guys, it doesn't matter what type of function we're talking about. So take out the word exponential. When we're talking about reflecting across y equals x, when we're talking about inputs and outputs transposed, what's the first thing that we should think about? Inverses, right? Hey, come on, Trey. I need them all. Hey, I need them all. Thank you, sir. Trying to look out for you. Alright, we are talking about inverses when we talk about reflecting across y equals x. So, I see a question of like, Cam, I think this is yours. How do you do exponential functions? What do you mean by that?
I don't understand anything.
Okay, I need you to be more clear. What do you not understand? What an exponential function is, how to make a table, how to make a graph. What do you mean? Okay, be more clear with your language, please. If I need to go answer other questions and come back to it, cool. But I need you to be more specific with your language. You can't just say all that right there. There's something that you know and there's something that you don't know. I need you to think about what you don't know. Use your language to describe what's up there. Thank you, Dave. Yeah. We're going to talk more about inverse functions later. We'll talk about domain range, x-intercepts, y-intercepts later as well. Thank you, Jay. Oh my gosh, oh, you're mean like right there. Thank you, thank you. Okay. And Mason, I'm going to answer your question when we go over the demonstrate your understanding as well. So, really quickly, those people who I said, hey, I'm going to talk about this for sure. So these questions right here, make sure I answer your question completely. Cam, I need you to continue thinking about what you mean by how do you do exponential functions. This will be part of today's lesson, but I don't know what that question means. How do I write an exponential function with a what?
Reference point.
Reference point. Got it. Yeah, we'll talk about. Actually, we're not going to do it with reference points. When we write an exponential function, I'm always just going to expect this, where what does A represent? The y-intercept. So you'll have a way to find the y-intercept. And then what does B represent?
The base, right?
That is the base, but what do we do with that base? It has a variable exponent, so what are we doing with that base, Janaya?
The B?
Yeah. What are we repeatedly doing with it? And by the way, Janaya, I need your headphones out. Thank you. Say again.
I don't know.
Okay, so let's engage in this conversation. Remember, it's raised to a variable exponent. Yana, what do we mean by an exponent? What is that? What is it? Constant multiplicative, or at least an exponent is repeated multiplication, right? So, Janai, if an exponent is repeated multiplication, what are we doing with this b right here? Repeatedly what? Multiplying. And so, Cam, you even answered this question right away. That's how I know you know something about this. I need you to figure out what question you have so that I can answer it. I can't reteach everything exponential, but try to think about what question you have with that. So, this, remember, what do we call the thing we repeatedly multiply by? The exponent shows me that I'm repeatedly multiplying, but there's a word up here that is what we repeatedly multiply by. Constant. So it is a constant multiplicative rate of change called a constant Factor. When we say exponential, we're talking about something that we're repeatedly multiplying by. Jay, I need your hood off, I need your hat off, I need your headphones out. I need you engaged in the learning process. Okay, I need the other headphone out, and I need the hoods off. Mr. Hinton walks by this room, you know, you and I both are getting reamed out. We ain't playing this game. Alright, let's see, I understand the vertical line test, but I don't understand the horizontal line test. When you have to put the plus or minus sign, I don't understand when to put it or why. Okay, so that'll come up with our conversation about on the demonstrate your understanding. And does that answer your question, Nate? Okay, so it looks like I've answered all the other questions except for the ones that we'll talk about in the demonstrate your understanding. So who was not here earlier when I passed out the demonstrate your understanding? We need to update our knowledge. So please take these, update that knowledge as we go over them. Simone, what group is Simone in? Thank you. And Simone, if I were you, I might turn that desk so you can see the board as we go over this. And Jaden. Jaden right here. And Amari. Okay, did I put your demonstrate your understanding already on your desk? Is that one yours? Okay. Alright, so let's talk about this demonstrate your understanding. So I want you to remember, like, I've already told you what I need you to learn out of this. And one thing I need to point out is you had your prayer model, you had your notes to your future forgetful self on this demonstrate your understanding. I need us, if we struggled on parts of this, we gotta do better notes to our future forgetful self. Not just writing down the what, but writing down the why. If you don't understand the why, or at least have notes about the why, Arion, need your headphones out, please, sir. If you don't have notes about the why, then it is hard to apply it moving forward. So, make sure you can explain why with these things. Restricting the domain of a function to make it invertible. I will say this. I decided to take out composing two functions to determine if they're inverses. That takes a little bit more time than we have. So if you want to scratch through the composed two functions to determine if they are inverses on that proficiency scale, that'd be a good idea. I'm just not going to assess you on that on the test. Determine if two functions are inverses graphically, and Mason, that's kind of your question, right? Determining if two functions are inverses graphically. We'll see that in the demonstrate your understanding. Graph the inverse of a function given graphically or tabularly. Solve an equation for the input to determine the inverse function. All that's on the demonstrate your understanding along with these vocabulary terms. We've got to know them. By the way, we're going to try to come back to extraneous, but you can take out the composition of two functions because we're not going to do that. All right, so here's the thing. Some of us legitimately struggle on number one. This is the thing that we studied and went over every single day, multiple days, and should have notes to our future forgetful selves on this, but some of us didn't earn the CE or higher, and we got to know this, okay? So Mason, give me one thing that you know about functions and their inverses. Just any one thing.
The inverse need to be completely opposite or transposed.
Okay, so inverses need to be completely opposite or transposed. Be careful with that word opposite. What do I mean by opposite mathematically?
Like the inverse.
Right, so the opposite of 5 is
-1.
-5. The opposite of -2 is 2. Right, so that word opposite in mathematics only means that. So we have to update our language. There is something with transposing, but, and by the way, I've already made scans of these, demonstrate your understandings. Update your knowledge as we go through these. Write down whatever notes you need because this is going to apply to today, which is why Chandler was asking about, will there be reflected exponentials? Yes, and so this is the foundation for that. So, transposing, what do we mean? What is Mason really referring to there? Can someone add on to? Okay, so what about those points? The so the what are those? What's being flipped? The
Inputs.
inputs. By the way, which variable is our inputs?
X.
X. And outputs, my y, are what?
switched.
I need a more mathematical term.
Transpose.
Transposed, right? Yes, they're switched, but the mathematical term is they are transposed. But why? Because the function is reflected across, what again?
Y equals X.
We got to know that, right? That is the foundation to an inverse function. If a function is reflected across the line y equals x, that's going to cause those inputs and outputs to transpose, and that's going to give me my inverse function. But are all inverses functions? So we need to go into some more detail. There's a lot more that we can say here about some inverses. Come on, someone give me something else. Let's continue updating that knowledge.
Each input maps to one and only one output.
Say it a little bit louder.
Each input maps to one and only one output.
Huh. Okay, Janiyah, what is Yana referring to when she says that each input is mapped to one and only one output? Do you remember what that's the definition of?
Function.
What is it, Janiyah?
Function.
Function. Okay, so we got to start with definitions, right? For a function, each input maps to
Y output.
one and
Oh.
only one. So that's why, though, based on this definition, right, those inputs and outputs are going to switch, right? Or they're going to transpose, is a mathematical term there. So what also has to be true for the inverse to be a function? What also has to be true to be a for the inverse to be a function? Council, you got a...
Zero.
Okay.
No, I got it.
I know. Come on. If each input has to map to one and only one output, what has to also be true for the inverse to be a function, Council? I can't hear you. You guys, speak up.
The horizontal line test.
Yeah, so that horizontal line test means that each output is what?
Oh, back to one input.
From one input. Because when I transpose my inputs and outputs, I need these outputs to only be from one input. Otherwise, these things don't work. Otherwise, the inverse is not going to be a function. What do we call it when each input maps to one and only one output, and each output is mapped from one input? There's a name for this.
Invertible.
It is invertible. So there's another name that I want to get to first. One-to-one. Remember, to be an invertible function, it has to be one-to-one, right? And so all of this has to be true to be an invertible function. And so some of us were asking about horizontal and vertical line test, I think. Yeah, vertical line test, but I don't understand the horizontal line test. I need to erase this for space. Don't let me forget to answer these questions, though. Okay? This vertical line test, right here, means that whatever this input is, has how many outputs mapped to it? Just one, right? This input has how many outputs mapped to it?
One.
Just one. And so, is this a function?
Yeah.
Yes, right? However, if I were to do a horizontal line test, this one output, right here, this one output has how many inputs associated with it?
Two.
Two, right? So when I reflect across the line y equals x, when I get the inverse, I'm going to get something that looks like this. And so if that one output had two inputs, that now means this one input has how many outputs? Two. So one output mapped from two outputs, or two inputs. And so that's what the horizontal line test is checking, because what's going to happen to the output and the inputs? They're going to be swapped, they're going to be transposed, right? So now one input will map to two outputs in the inverse. So the horizontal line test checks to see if the inverse will pass the vertical line test. That's what the horizontal line test is testing. The horizontal line test is testing if the inverse will pass the vertical line test. Because when you reflect across y equals x, what does a horizontal line become? A vertical line. Do I need to clarify or update that at all? By the way, Julian, when we're talking about number one here, it might be a good idea to update your knowledge some. But I just finished talking about this. Do you have all those notes? Oh, okay.
So that's the inverse, so like that is fine, that would be transposed.
So we're going to talk more about that in a second. I'm just illustrating right now that horizontal and vertical line test idea, and how we're getting invertible functions, stuff like that. The other thing I would point out is, here is a cubic function, right? Y equals x cubed. Does anyone remember what its inverse function would look like? So the inputs and outputs would be transposed, right? And so instead of being more vertical, it's going to be more what?
Horizontal.
Horizontal, okay? But before I do that, I want to point this out. Is this a function? One input maps to only one output.
Yeah.
Yeah, everywhere I look in the domain, that's true. Each output is mapped from how many inputs? Only one, right? That is passing the vertical line test. So for its inverse, it'll pass the vertical, or it's passing the horizontal line test. So for its inverse, it'll pass the vertical line test. So this is just a rough sketch, Mason. But remember, I can use my line y equals x to think about where the inverses would end up. And so like right here, this point is going to be reflected across this line, perpendicularly and about the same distance. Perpendicularly and about the same distance. Perpendicularly and about the same distance. And so this is not a perfect graph, but, whoops, this is roughly what it would look like. So if you go back to the definition, the idea is reflected across y equals x, all you have to do is reflect the same distance to the other side of the line y equals x. So that's a way to visually check it right away. Well, I'm going to look at it more accurately in a second. But that's that cubic, right? The cube root. Remember, the inverse of x cubed is the cube root. Okay? So I need to recognize that. Think that's all things about functions and their inverses. What questions do you have about that? So we all updated our knowledge to make sure we can get CEs and higher, clear evidence of understanding, if I ask this question again, right? Okay, I'm going to move forward if there's no questions. So, we already talked about it. The issue here, is this function right here invertible?
Yes.
Right now?
No.
Why not?
You
You gotta restrict that side.
Okay, why do I need to restrict the side though?
The invert.
Well, it's not invertible, but to make it invertible, but why is it not invertible right now?
Horizontal line test.
So the horizontal line test shows it. Now, be careful, right? The horizontal line test tells me it's not invertible, but the reason it's not invertible is because if I were to, remember we're going to reflect these points, right? So we're going to transpose these points, 0, 5, and I believe this is 5, 5. And if I transpose those points, that point stays right there. And what does 0, 5 become?
5, 0.
5, 0. So 1, 2, 3, 4. Oh, that's wrong. That's 6, 5. And so when I transpose, this gives me 5, 0 here. And what does this become?
5, 6.
5, 6, so 5 and 6. And so you'll notice, I'm just going to do one more point. This is 3, negative 4. What does that point become? Negative 4, 3, so negative 4, 3. And so it becomes this. Is this inverse a function?
Oh, I didn't guess the part, I didn't do, I just wrote it straight line.
Well, this is not correct. My point is, if I were to reflect this parabola across y equals x, is its inverse a function now? No, right? Like that's the whole idea. But notice, Mason, this answers your question. How do we know graphically if they're inverses? Well, I literally just took the points and did what to them? Well, I did, what did I do to the points? I transposed my inputs and outputs. That's it. I can graphically check by sketching y equals x here. Notice how these are reflections across, right? But that's all I would do. But notice the easier way with our graph and with our table is to transpose the inputs and outputs. That's it. Don't make it more complicated than that, okay? But notice, Trey, like what we said is, that's not a function, right? That's the problem here. Because, and we just looked at a definition, this one output is mapped from how many inputs? 2. So when I transpose, that means one input's going to have how many outputs? 2, right? That's not a function. And so we said to make it invertible, we got to restrict it. So where am I going to scratch out this graph to make it invertible? The left side all the way to where?
Vertex.
The vertex, right? Now, does it pass the vertical or the horizontal line test so that it's 1 to 1?
Yes.
Okay. So now the function is 1 to 1. The reason why is the whole point, right?
Well, you were supposed to say why on that question?
What do I always want? Evidence of understanding.
Yeah, I got D on
The
there.
why is always the evidence of understanding.
So that's why I got D.
Part of it, did you also write the restriction in interval notation? So what is
What you
my,
mean?
well, what is my domain now? So what I'm talking about is just, hey, here's this point. So what is the domain of this function now?
3 to infinity.
So the lowest x value, the minimum x is
3.
3. What's the maximum x? Infinity. Does it ever quit going to the right? There it is.
That's what I got now.
Okay, then it's the reason why. You might have also made a small mistake in there somewhere. I'll have to look at it. Was it DE or DE plus?
D.
I'll look at it. Remember, an interval notation is always a minimum to a maximum. And if I want a domain is all about the what? And what's my lowest x? What's the first x I get to? Right here. And what's that x? And if I'm talking about x, I'm looking to the right. Does it ever quit going to the right? So what is that maximum x? No, maximum x. Does it ever quit going to the right? It's what? Positive infinity. Never quits going to the right. Never, ever, ever, ever.
Yeah, I got that, but I just didn't explain.
Okay.
What?
Then it feels like it should be a DE plus, but I'll come and look at it. You always got to justify why. Remember, I want evidence of understanding. So graphing the inverse. So what you can do very easily is just take the points on the graph and transpose them. Make sure you identify each of the easy points though. So I start here at the vertex. I can see a clear point here. I can see a clear point here. And I can see a clear point here. And for those of us who earn CEs and CCCs here, what did y'all do to make it clear that you had evidence of understanding for graphing the inverse?
I made a table.
Tables, right?
Yeah,
So, x and f1 of x, inputs and outputs. So we got 3, negative 4. Say again.
3,
Ken, what were you saying?
5, 0, 6, 5.
Say again, Ken. Okay. And you didn't have to use this notation, but I will point this out. Why am I using this f1 with that superscript negative 1 of x?
That's the inverse.
That's the notation for the inverse of f of x, right? It's the result of transposing. And so what points do I now have? Negative 4, 3, yep, good job. Negative 3, 4, 0, 5, 5, 6. And so a quick note is transpose. Right? Just a quick little note to tell me you understand why you're doing what you're doing, and then you just graph your points.
That's why you got a big old Y sign on that thing.
Probably. Negative 3, 4, 0, 5, and 6, no. What was it? 5, 6. Now, I'm going to point this out. I need you to be careful here. This has a very grave error that a lot of us make. What's wrong with that graph? It's right here. I'll say that.
Yeah, you put a P right there.
Uh-huh. Ah,
Insert.
I circled it. So you made that mistake. It's okay. It's one to learn from. But guys, what did this point correspond to? That was the vertex. Did we go past this point in the original function?
No,
So can I go past that point?
no.
That's that square root function right here. It stops at that vertex.
Oh,
Ah,
why you started a little line on that?
yep.
I didn't even go to
If it goes past it, that's a problem. It's mathematically incorrect. We gotta be careful about it. Details matter. What questions do you have through number 3?
I don't know. I'm just gonna get a DE.
I'll come look at it after class. We got some other stuff we gotta cover. Okay, Mason, does that answer your question though about graphical? That's it. That's what we did the whole time leading up to this. It's just understanding that we want to look at those the inputs and outputs transposing. Please notice, like, if you understand the definition of these functions, everything else flows naturally out of it. If you understand that the inputs and outputs transpose because we reflect it across y equals x, there's lots of ways to tackle it. But that's it. The only thing on top of that is we have to have that one-to-one function for it to be invertible. And so we have to know how to restrict the domain for that. Okay. Number 4, writing the equation. This is probably the one that I recognize would give students the most trouble. It typically is, so let's learn from this one. But once again, going back to the foundations, Sean, what is an inverse function? What's the key to it? Needs to be one-to-one, right? To be invertible, but like, what is an inverse function? Like, what is it? Did you make these notes under number 1 when we went over it? There's one sentence I'm looking for. What is it? Okay, so we got to know this off the top of their head. I told you this earlier, Jaden. Say again. My question is, what is an inverse function?
An inverse function reflects across the Y if it transposed to inputs and outputs.
It's a reflection across y equals x, so the inputs and outputs transpose. You got to know that instantly off the top of your head. If I ask what an inverse function is, if a future class asks what an inverse function is, you got to know it's just an input, or it's a reflection across y equals x. So what happens to my inputs and outputs? They transpose. So when I look at this equation, right, because f1 of x is just y, equals x minus 3 squared minus 4, what's the first step?
Push the one that
Transpose them, right?
Bless you.
Bless you.
That's all you had to do?
Nope, not done yet.
ever.
Because remember, we want an equation to be y equals, right? That's a form of a y right here. My input is x, so my output is y. So now what I need to do to know what y is equal to? Inverses, right? Don't forget to pay attention to your order. It's y minus 3 first, and then y minus, because of the parentheses, right? Parentheses, then exponents, and then after those exponents we have subtraction. So the last thing being done is that minus 4. So what do I need to do? Add 4. But whatever I do to one side of the equation, gotta do to the other. That's that property of equality. Whatever you do to one side of the equation, you have to do to the other. It's a property of equality. That's just the name of it. What's the next inverse? When I have a square, the inverse of a square is a
Square root.
square root. And whatever I do to one side of the equation, that I do to the other, that's called a property of equality. Now, someone was asking earlier about the plus or minus. Technically, when we take a square root, you always need a what? Plus or minus. But if we think about this for a second, that means one input is going to have how many outputs? 2. Do we want 2 outputs?
No.
Because that would not be a function. In fact, we only have the top half of this sideways parabola, so I don't want positive and negative, I just want the positive. That's it, right? Understanding that, hey, when you take that square root, technically it's a positive and a negative, but because I want my inverse to be a function, I just need the
So that's all the
positive.
answer is?
Huh?
That's the answer?
Well, do I know what y is yet? What's the last step to find out what y is equal to? Add 3. So, square root of x plus 4 plus 3, because that's not underneath the square root, equals y. And so, the absolute last step is, I want to indicate that it's an inverse function. So instead of saying y equals, I'm going to say the inverse of f1 of x, which the only reason why it's f1 like that is because I put it into the calculator and that's how the calculator does it. It could have been inverse of g of x or anything like that. The key is understanding my inputs and outputs transposed.
So that's it.
And then I solve for y. Yep. Say again.
You just solve for
Right, that's what we did. When you use inverses and properties of equality, you're solving, and we solve for what y was equal to. Right?
I got that one before.
So we just learn and we grow. Say again. Like this versus this. Like me starting with a square root and going to a square. What do you mean then?
Oh, no, no.
Okay. All right. So we've actually already talked about the. Actually, let me ask. What questions do you have before I move forward? I would expect some questions. Say again. With what? Yeah. Before I get to number 5, what questions do I need to answer? Yes, Chandler.
When you put plus 3 on the minus 3.
Yeah.
Um,
Remember, the whole point is to create that 0 there, a 1 here. But what's your question?
yeah, where does the other 3 go?
Remember, it's right here.
Yeah.
When I add 3, so negative 3 plus 3 is 0. That's the whole point of opposites, was to make a 0. And so whatever I do to one side of the equation, I have to do to the other, right? Since this is not under the square root right here, I can't put it under the square root, so it just stays outside of the square root. Whatever you do to one side of the equation, you have to do to the other. Is that the plus 3 you're asking about, or the other 3 you're asking about?
The one under the square root.
There isn't one under, yeah, this one is this one, right? I can't put it actually under the square root. It's outside of the square root.
So where do you go from there?
You're done.
Um,
There's no way to simplify it. That's why I then wrote this, right? I just put the inverse notation there.
Will it always equal like a plus? Like, does it ever?
The positive instead of the negative.
Yeah.
I'm not going to ever give you a situation where it's not that. So technically, yes, but we don't have enough time to go into the small details of when it is or is not. I will say the difference is if it was concave down, we would use the negative. Which makes sense because it's concave down, but I'm not going to test you on that right now, okay? All right, so let's get into domain and range. So Kim, you said you need help on this, right? What do I mean by domain though? It's the set of all what? X values, right? Look at my restricted function. We already talked about it. What is my lowest, my minimum x? We already did this one. What is it? 3, okay? What's my maximum x? Notice how I keep labeling these things, guys. This is evidence of understanding here. What's my maximum x? Infinity. And if domain is x, what is range? So what's my minimum y value? What's the lowest y value? Tell me when I start getting to my function. Negative 4.
Wait, how do we get?
Okay. Sure you don't want to ask the question.
Oh, them brackets.
So the brackets are whenever you actually have the value. See how there's an actual point right here? Because there's an actual point, I use the brackets. But like, can you actually ever get to an infinity? So that's why I use parentheses on the infinity. Jaden, were you asking a question?
I thought I was wondering if
The minimum x? Well, but look, we no longer have any of this, right? So my x starts, so if I come across here, tell me when I get to a point on the graph. Right there, what is my x value? So the minimum x is 3. Well, it's whatever the leftmost or lowest x value is. So you just keep going, because you always start from left to right. So you always keep going to the left until you get to the first point. Okay? And Ken, we are going to see today a case where you would use parentheses even though you actually have a number. So it's when you actually have the point, that's the key there.
I had a question.
Yes, ma'am.
If that parabola was over there, would it be negative?
So like if we had not this side but that side,
Yeah.
so like if I use this side instead, where does it start? All the way over here, which is negative infinity, and it would stop here at a positive 3.
Oh, so it's a family because of that.
Because it keeps going to the right. Remember, domain is all about the x, range is all about the y. Yes, Chandler.
Huh?
Oh, you're just stretching. Caitlin.
Could you go over the domain again? Because I have infinity in front of the 3. Like I
You
have a
always do a minimum, then a maximum.
See, I put 0 because I thought we were going on the main point, which was like 0 5. So I was like.
But remember, there's still a graph to the left of that, right? Technically, it never quits going left. We have to go off the restricted domain to make it invertible. Yeah. But
I
that's the
still
way I
got
did
it
that.
wrong, but I guess why I got 0.
Does that make sense though? But again, and here's something I need you to explain. Like, you're explaining these words right now, right? Did you write that down on your paper so I understood where you went wrong? Write down your explanations, why you're doing what you're doing, what you're thinking about, because that can still be evidence of understanding. If you don't write that stuff down, it just looks like random numbers. Show me your understanding. All right, x-intercepts. Does the original function have an x-intercept?
Yes.
So I was 0.
Yeah, it intersects the x-axis, right? What about y-intercept?
I confused myself with that.
No.
I read it.
So, notice, do we have any of these points right here?
I confused.
So do we have the y-intercept?
No.
No, yeah, that's why I confused myself.
So, we don't have one.
Would it always be like that?
Hmm?
You know, always be like that?
No, but I mean, like, you can look at the graph and see where there's a y-intercept, right? If I no longer have this, does it intersect the y-axis? Right? Right, remember how we restricted the domain? We don't look at any of this graph anymore. We only look at the right-hand side. There was no y-intercept then.
Definitely.
Right? Okay? So, does anyone remember the quick detail to make it easy to identify these features for the inverse, Chandler?
Why is there a bracket and a parenthesis?
So, use a bracket when so this is only for interval notation. So that's a point, not interval notation. You always use a bracket when you actually have the value. Use a parenthesis when you do not actually have the value. So can you ever get to infinity? No, so you can never get there, so we always use a parenthesis on infinity. Do we actually have that value of 3 in the domain? Do we actually have a 3 right here? Yes. So that's why I used a bracket. Okay? Does anyone remember the quick detail to help me identify domain or the features of the inverse? Does anyone remember the quick little detail to help me identify the features of the inverse?
Y equals x.
Well, it's reflecting across y equals x. It's causing my inputs and outputs to transpose. So what does that end up doing to my features?
It switched to the domain and range.
Switches them, right? Okay?
I do this.
So, this domain becomes my what?
Range.
range.
Oh, my God.
Why?
Oh, my God.
Look at it. What is my lowest y value? 3. Does it ever quit going up?
No.
So what's my highest y value?
3.
Infinity. See how the domain and range switch because my inputs and outputs transpose.
Oh, my God.
So what's this domain going to be?
Negative over 2.
That don't make no sense.
Yes, it does.
No, it's not. I got it wrong.
Oh, how you got it wrong? So what is this x-intercept going to become?
0, 5.
Well, 0, 5, which is going to give me a
Minus.
y-intercept.
And we won't have no if.
And we don't have an x-intercept.
Oh, my God.
Features, switch. With inverses. I hear someone's music, which means they cannot hear us. Is that your music?
I know who it is, but I ain't gonna shoot.
Sean, you got some headphones in? But headphones out, dude. We got a week. We gotta learn some stuff. So, feature switch with inverses. So, quick question. Are there any questions I have not answered from the bell ringer? What are your questions from the bell ringer that Arion, need your headphones out, my guy? Arion.
Oh, God, you just did that city turkey.
Yes, Janai.
Can you do number 4, but like with a different with different numbers? Though?
Like an equation?
Yeah.
We're gonna practice some today with a new
You
function.
got what I'm
Okay.
saying.
But I'll do one really quickly. But it doesn't change. The idea is that I'm going to transpose my inputs and outputs and use my inverses, right? So let's look at one really quickly to answer that question. So let's say that, and this is actually going to be very different, but I just want you to see it does not change. 3 times the cube root of x plus 2. Okay? So I made up this new equation here. Y equals 3 times the cube root of x plus 2. And so if I want the inverse function, Trey, we should probably learn this. Okay? So what's the first thing I'm going to do if I want the inverse?
Transpose y x.
If I want the inverse, I'm going to transpose. So what is this y going to become? What's this x going to become? Now, what do I need to use? Inverses. Now, we just need to pay attention to the order here. What's happening to y? It's being added by 2. I made it up because of Jania's question.
Is that 3?
Yes, so this is a cube root, not a square root, right? So y plus 2, then it's the cube root of y plus 2,
Wait, no.
then it's times 3, right? So what's the last operation happening, Janai? If I follow my order of operations.
I wish.
So what's happening first to this y? It's being
added by 2.
it's being added by 2. What's happening to y plus 2?
Y plus 2 square root.
Close the cube root, right? And what's happening to the cube root of y plus 2?
Multiply.
By 3. So what's the last thing happening? Say again.
Would you divide?
The inverse of so I'm just pointing out the last thing is multiplication. The inverse would be that division. Now I use that reciprocal, but remember that fraction bar just means divide, right?
Right.
Okay, so 3 divided by 3 is 1. Property of equality, so 1/3 x equals the cube root of y plus 2. Now what? What's the last operation?
The cube.
The cube root. And what's the inverse of a cube root? Right, so remember, it's just that power, right? So the inverse of a cube root is just a cube. Whatever you do to one side, you have to do to the other. And because these are inverses that are going to cancel each other out, I'm almost there. What do I now need to do?
Subtract 2.
Subtract 2. So 1/3 x all cubed minus 2 is equal to y. Notice, all I have to do is use my inverses in the right order. Okay? So if you understand transposing inputs and outputs, you just solve for y after that. Okay? But we're going to get some more practice with that in a second. We should get there today. Alright, what questions do you have before we continue with the inverses of exponentials?
I thought you wanted to do with the one on the back.
Yeah, let's look at it.
I'm saying, but
Oh,
you-
remember I said at the very beginning of class that we don't have time, so I'm cutting that from, that's why I told you to scratch through it on the proficiency scale.
That right there?
That's the determining if functions are inverses through composition. I didn't do it. Okay. So, as a recap, right? Linear versus exponential. We did a whole lot with linear versus exponential. Hold on 1 second. What are some of the things that we need to remember about a linear function?
Constant additive.
Constant, additive, rate of change, okay? So, how's that in contrast? It's going to the right, isn't it? So, it's going to the right. You always read from left to right. So the lowest x is -4. And it keeps going right to positive infinity. Okay. All right. Hey, Julian. Eyes and ears up here, my man. So linear, constant additive rate of change, graphing a line, y equals mx plus b, and that's in contrast to an exponential function. By the way, you need your logarithms and log functions for your model out. You need, I would have my pages from the textbook out. Okay? So, we talked about exponential functions. We talked about those exponential functions a little bit more on Friday, I believe. Yep, Friday. But exponential, what we've always known is that it has a what type of rate of change? Constant multiplicative. They're repeatedly multiplying by something, okay? So this might help Cam's question. Just as a quick table. That's what I'm about to do. Does anyone see what my constant multiplicative rate of change is?
500.
Multiplying by 1/2, right? So notice my constant factor, my b, is 1/2. Is that making my values bigger or smaller? So it is decaying. And you see how that base is between 0 and 1? So if you multiply by something between 0 and 1, it's going to make those numbers what?
Go down.
Smaller, right? Decrease, decay. In this case, yeah. Right? So remember, y-intercept is 2. And my base, my constant factor, is 1/2. And if I'm multiplying by 1/2, what's that number going to do? It's going to get smaller. If I take, let's say, 9, and I multiply it by 2/3, notice, what's 9 divided by 3? And then 3 times 2? And if I take 6 and I divide it by 3, I get 2, and 2 times 2 is 4, and then I'm going to get 8/3 if I continue that. So notice, here's my focus, Cam. Is this decaying or growing? It's decaying. Is that number between 0 and 1 or greater than 1? So, a constant factor, a base between 0 and 1, causes the function to decay. Yes, Snake, repeat.
No.
Oh, just right here. A constant factor, a base between 0 and 1, causes that exponential to decay. I believe there's a section here about linear versus exponential. Actually, exponential functions and their features would be a good place as well. So the contrast, if I multiply by 2 and multiply by 2 and I multiply by 2 and I multiply by 2, is that going to cause the values to grow, or is it going to cause the values to decay? It's going to cause them to grow. So a base greater than 1, a constant factor greater than 1, is going to cause the values to grow. So, out of the textbook, we need to be looking at M3-107 a little bit after that. I'll wait a second for you to get those notes down, but then we need to flip to that page in the book. It'll be a little bit after that in a second.
What page?
It's up there, M3-107. We should have torn that out last week. It'll actually be, it's actually page 110. So once we get going, we'll look at 110. I would recommend it because we're about to get into is the logarithm side. Yeah, we're about to start talking about those logarithms.
So what test are we needing next? What were you thinking of this?
We are taking a test on inverses and logarithms together. No, not together like that. All right, so page 110. Bless you. So we should already have this. I'm going to write the answers for the ones that we should have already done. I need you to ask the questions that you need. But here's my domain, and you can see sketches of the graphs to confirm this over there.
Would that be a bracket?
Those are not brackets, and I'm going to explain why in a second. I'm going to talk about end behavior because that is something that we struggled on the last test. By the way, with the growth, is it increasing or decreasing? It's increasing, right? If I draw a tangent line, remember we talked about that, the slope would be positive, so it's growing. And so remember, it's domain intervals, and it is growing everywhere. So the domain interval of increase is negative infinity to infinity, based on the graph of the growth versus the decay. And the one homework assignment I asked you to do over the weekend.
It was Mother's Day weekend.
Oh my gosh, that means Sunday's out. But Friday, Saturday. I also imagine your mom would want you to learn something until you're ready for tests, but that's just me.
I got my mom something.
Yeah, I was there at work the whole. Yeah, that worked today.
Hey, if we had tried this during advisory on Friday, then we still could have gotten it done. Notice with the decay, it is always what? Decreasing, okay. I'm going to tie asymptote and end behavior together in a second. But Nate asked the question, shouldn't this 0 be a bracket, right? I want you to notice, it approaches the x-axis, but does it ever actually get there?
No.
Does it ever get to the x-axis? Or does it just get close? Remember, on the x-axis, what is the y value?
0.
The y value is what? 0. So it gets close to a y value of 0, but does it ever actually get there? No. And here's one reason to think about it, or a way to think about it.
Why is it 1?
Well, because it gets to 1, but does it get below that y value of 1?
No.
Yeah, it does. So watch this. 2 times 1/2, what is that? 1. What's 1 times 1/2? Or 1/2, right? What's 1/2 times 1/2? What's 1 times 1? 1. 2 times 2?
Okay, 4.
1/4 times 1/2, then would be 1/8. So first off, notice, Cam, how it's getting less than 1, isn't it? All these values are less than 1. But if I keep multiplying a positive times a positive, it's always going to stay what? Positive. So what's it never going to get to if it is staying positive? It's not just not going to get to a negative, it's not even going to get to 0. If it is positive, it's never going to get to 0. So, do we actually have the y value of 0? No. We need to recognize that we do not actually have the y value of 0. And so, this is where the word asymptote comes from. So an asymptote is a line or a curve, a function approaches. What do I mean by approaches? Okay.
Gets closer to.
There we go. So when you approach something, it's a line or a curve that a function approaches at an infinity. So over here on as x goes to negative infinity. By the way, notice that language I just said, as x goes towards what? Huh, what should that remind me of?
Notation.
In behavior, right? As x goes to negative infinity, what is my y going towards? What's it getting close to? It's flattening out, getting close to what? What is this line right here? The x-axis, which is a y value of? So as x goes to negative infinity, y goes towards 0. Can't remember how we just talked about it getting smaller and smaller, but what does it never get to? So it's getting smaller and smaller. It's getting close to 0, but does it ever get to 0? So it approaches 0, which is why the asymptote is y equals, any guesses? 0. Right? That's the value that the function is approaching. It's approaching the 0. By the way, this can go under growth in behavior right here. So, one thing I want to caution you is, a lot of us forgot my notes that I said day after day after day, that in behavior is not just same direction, opposite directions, it's not just up and down. In behavior is what is happening at the ends of the graph, and we have to use this notation here. Because notice, is this the same in behavior as what we saw with polynomials? Y go into positive or negative infinity? No, we have to actually look at the ends of the graph to see what's happening. This is my left hand in behavior. And so for that growth, what is my right hand in behavior? What's happening on the right side? What is x going towards on the right side? Yeah, it never quits going right, so it's going towards infinity. And what's y going towards? Infinity. It never quits going up. And if you understand in behavior, ladies and gentlemen, domain and range are easy. What's my lowest x value?
Negative.
What's my largest x value? And what's my domain? Negative infinity to infinity. What's my lowest y value here in the in behavior? Zero, right? Now it's not always going to work like this, but zero's right here. What's my highest y value?
Infinity.
So what's my range?
0 to infinity.
0 to infinity, right? Never don't update Microsoft Office. Okay? I got it. Okay? So, for the decay, notice how much has changed with my decay? You say a lot? Let's look at my left hand in behavior. As x goes towards, on the left-hand side, what is x going towards? Is that arrow, so is it ever going to quit going left?
No,
So what is x going towards?
infinity. A negative.
No, left. Negative infinity. And what's y going towards?
Infinity.
See, that's going up, so it's going to infinity. Right-hand in behavior. As x goes towards, what's happening on the right-hand side?
Infinity.
Infinity. What's y going towards? So that's my in behavior down here. Notice that means also at an infinity, what is the line that my function approaches? Y equals what? What line is it approaching at an infinity?
0.
0. And I need you to hear me very clearly on this. This is too much information to memorize. But if we understand our definitions, if we understand what the things mean, you can see it and you can write it out. You can't memorize what the asymptote is always going to be because it's going to change based on the function. But if you understand what in behavior is, and just, hey, in behavior is just looking at the two ends and saying as x does this, y does this. If you understand in behavior, then the asymptote is a natural part of it. At this infinity, my y is approaching 0. That's my line, y equals 0. That's it. So if you understand these features and what they mean, everything else is natural. What questions do you have about these features?
There's a lot to remember.
But remember what I just said, Janai, is this. It's too much to memorize all of it. But first off, if you know it's an exponential growth, can you kind of sketch out a graph of it?
Yep.
And if you can sketch out a graph of it, can you see the end behavior?
Yes.
Like you see the ends, right? Right here and right here. So can you tell me on the left-hand side, as x does this, y does this? Because that's it. Like if you can label it, if you can name it, it's telling you what to do. Right? If you can sketch out a graph, maybe from a table, or you just put an equation into a calculator, sketch out the graph, you just tell me what the end behavior is. You've learned about intercepts, right? Okay? You learned about domain and range, right? You've learned about intervals of increase and decrease. Maybe you still need to work on this some. But that means, and we've looked at end behavior before, so the only absolutely new thing is asymptote. But what is determining the asymptote? The end behavior. So it's not memorizing all these things, it's seeing the connections and using them to help us remember it. But if you can have a graph, you can see it and not just memorize it. You just have to know what the features mean. If you understand what the features mean, it's easy to identify from a graph. I'm not going to go through all of this. This is number 10. I just want to point this out, just glancing at these things. Is this exponential growth or decay? Why is it growth?
It's hot.
But just constant multiplication doesn't make it always growth. What makes it growth?
A positive.
A positive.
Not a positive. Guys, the information's over here. Something about that rate of change. What's repeatedly happening here? I'm multiplying by 2. If you multiply by 2, is that going to make things smaller or bigger?
Bigger.
Bigger, right? Remember that base is what? Greater than 1. It's not about positive or negative. The base is greater than 1, or it's between 0 and 1. It's just going to be like a page or so later. G of x, growth or decay?
Growth.
Growth. The base is what?
Higher than 1.
Greater than 1. Growth or decay?
Decay.
Decay. 3/5. That's less than 1, right? Don't stress it too much. Hey, just right here. Just right here. Base is greater than 1. Base is greater than 1. Base is greater than 1. Base is less than 1. Base is...
Less.
1.3 is less than 1?
I'll check.
It's greater than 1. So, growth, growth, decay, growth. I just want us to recognize
Grow, decay, grow.
that they all have that growth or decay there. Now do notice, all of these bases, are they positive or are they negative? They're all positive. Notice It is not exponential if the base is 0, 1, or less than 0. It is not an exponential if the base is 0, 1, or less than 0.
That was my teacher for year for seven.
It's a good note to have. Now we need to get to Chandler's question from the very beginning of class. But before that, what questions do you have? Okay? So Chandler, what was your question? Beginning of class, are we ever going to do what? Reflections of expo. Reflections of exponentials, okay? So page 125, number lesson 3, what is it titled? Return of the inverse. So apparently we're going to find out about some inverses, a new inverse, right? The inverses we did before were of the power functions, right? X squared, x cubed, x to the fourth. We did inverses of those power functions. Which, by the way, what type of function was the inverse of a power function? A radical function, right? A square root, a cube root, fourth root. Now, we're going to look at inverse of these exponential functions. First things first, right? So this is getting started. So we have a table, and we have a graph for this exponential function 2 to the x. Okay? So here is 2 raised to the x. How do I know that this is an exponential function right here? Not just because of the curve. I would agree with you. Raised to the... Remember that variable exponent tells me repeated multiplication. Specifically, KK, what am I multiplying here in this equation?
2.
KK, what did you say? What am I repeatedly multiplying by in this equation?
We have 126, right?
Yep. 2, right? 2 raised to the x, repeatedly multiplied by 2. We can see this in the table, right? So notice, Cam, it's not just, hey, it's got an exponential curve. In the table, what can I see? Repeated multiplication, right? In the equation, I can see that repeated multiplication. So it's an exponential function, and so now we have, what does that notation mean? This right here?
The inverse of that function.
That's the inverse of f of x, right? Graphically, Mason, how do I know that those are inverse functions?
I had them on mine. It's basically, it's just flip-flop, so you basically just do the inverse of the numbers.
So there's another word for that I want you to think about. It started with a T. Transpose, right? What does 0, 1 become? 1, 0. Huh. There we go. What did 1, 2 become?
2, 1.
2, 1. What did 2, 4 become?
4, 2.
Do we see all those points being transposed? Notice also that means it was a reflection across
Y equals X.
y equals x. So, Chandler, you tell me, are we going to do reflections of exponentials?
Yeah.
Yeah, anybody know what that inverse function is going to be called?
Reflection of exponential.
Yeah, but what is that reflection across y equals x of an exponential going to be called?
Reflection of exponential.
No.
1 to 1.
Remember, the inverse of our polynomials were the power functions were radicals.
A lot of rhythm.
It's called a logarithm.
Oh, the L word.
The L word, right? And so we need to just recognize logarithm is the inverse of an exponential. And so there's a lot of implications that we need to recognize out of this. Cannot tell you how many times I even work with students in Alpha Theta, the Math Honor Society, they're like, yeah, I really just still don't know what a logarithm is. And that's because we try to teach kids to memorize it. But at the end of the day, what is a logarithm? It is just an inverse of an exponential. So what were the inputs become the
Output.
Output. So if we understand that idea, you understand what a logarithm is. We're going to practice some with it. But it's just the inverse of an exponential. But that's going to bring up some features that I want us to think about. I believe this is there in the getting started as well, isn't it? The features piece here. Yes, Mr. Kenny. Thanks, guys.
Yeah, Mr. King.
There we go. Okay. Bottom page, features, right? Let's look at our exponential. We just did a whole bunch of features for exponentials. What is the domain for f of x?
Negative infinity is like positive infinity.
Is the lowest x value negative infinity?
No, it's 0.
So remember, we're talking when we say domain, we're talking about which values? Does it stop at an x value of 0 right here? So minimum x, and this is why I like to label it. So Yana mentioned 0 earlier. Does anyone know what the minimum of 0 is? What that's for? It's for the y, isn't it? Right? Like, does it ever get to the x-axis? So the minimum x is, or minimum y is 0. Yep. Is it at the very bottom of that page? Isn't there a table down there?
Yeah, I didn't raise it.
Yeah.
Negative.
And so I want us to recognize this. Des,
And
do you know what? Say again.
They gonna be able to say,
Yes.
whatever we got with it.
Yep. Des, the inverse of f of x. Do you know what they are without even looking at the graph? Any guesses or predictions? Say again.
They transpose.
So remember, the inputs and the outputs transpose, so my domain and range are going to switch. So what should this domain be? Just looking right here. 0 to... So let's look at that. Is that true that the lowest x value looks to be 0? See how it's approaching this y-axis? And what do we know about the x for every y-intercept that's ever existed? The x is?
0.
So is the lowest x value 0? Yeah. Okay. So what should my range be?
Hey, what you doing, dude?
Negative infinity to positive.
So, looking at my graph, we cannot forget range just means what? The y values. What's my lowest y value for the inverse? Yeah, does it ever quit going down? No, so it's negative infinity. Does it ever quit going up? Nope. So it's positive infinity. And so, Janai, I know you were saying earlier, like, it's a lot. It feels like a lot, but notice I'm not just making these numbers up. I'm basing it on the graph. I'm never going to ask you to identify these features without the graph. And so if you understand what domain is and what range is, you can just look at the graph.
So, they gonna be opposite here too? Like, they just switch?
Let's find out. When you say, what are you referring to when you say they switch?
Like, how the domain and the range switch for the physical problem.
So, yeah, remember with those all the inverses we studied before, didn't the inputs and outputs transpose? So the domain and range switch?
Yeah.
Aren't these inverses?
Yeah.
So are they going to switch?
Yeah.
Okay.
Yeah.
Right, so this is why I say, like, it feels like a lot to memorize, but notice it keeps going back to the core definition of an inverse function.
Yeah.
If you understand what an inverse function is, you can understand logarithms.
Yeah.
Y-intercept. And actually, I'm just going to say intercepts. Scratch out the y-intercept. Does the original function have an x-intercept?
No.
No. Right? X-intercept, none. Does it have a y-intercept?
Yes, 1.
Be careful. I need something else with that 1.
0.
0, 1. There we go. So, what would my x-intercept be for my inverse function? Close. Would my inputs and outputs transpose? Do we see a 1, 0 right here? Yeah. What about my y-intercept? None. Does this function ever intersect the y-axis? Never gets there, right? It gets close, but it never gets there.
It is 0 and 1.
So yeah, remember that it's a y-intercept, so it was originally 0, 1 for f of x.
Yeah.
And then transposing.
Bet.
Again, the graphs can change based on what are called transformations. You can't memorize all these things. But if you understand what we mean by x-intercept and y-intercept, domain and range, and how those inverses things transpose, the rest of this becomes pretty straightforward. Alright, I'm going to skip asymptote, because does anyone remember what I said the asymptote is directly connected to? In behavior. So you know what I'm going to do first? I'm going to do in behavior before I do asymptotes, every single time. I'm going to do in behavior before I do asymptotes every single time. So I'm going to come back to here though. Let's talk about intervals of increase and decrease. So an interval of increase, so first off, this exponential, is it increasing or decreasing? That's increasing. What are, and don't forget I like to say domain intervals. And so where does it start increasing? Does it, yeah, so when I look at it, it starts increasing all the way over here. It may look pretty flat, but it's actually increasing because it's always multiplied by 2. Where does it stop increasing? Does it ever quit going to the right?
No.
Does it ever quit increasing all the way through?
No.
No. And so now my inverse function.
It's increasing.
It's increasing as well. Does it ever quit increasing?
No.
No, notice it, no matter where I look, you see how it has that positive slope idea?
No.
Okay, so it's increasing. Where does it start increasing? What's the lowest x value?
Negative infinity.
Does it go all the way to negative infinity though?
No.
Are you talking about because it's going down?
Yeah.
But remember, it's always a domain value, right? So what's the lowest x? Does the graph exist here?
No.
Tell me when I get to where the graph starts.
Oh, zero.
Ah, it starts here at that 0, doesn't it? Okay, so it's from 0 to, where does it stop increasing? I say, does it ever quit going to the right? Okay. And so I'm going to do this before the asymptote. And I know I keep coming back to Janai, but this is for everybody. When I look at my graph, that's how I see my end behavior. Circle the ends. There's my left hand end behavior. As x goes towards what? What is x going towards here? Negative infinity. What's y going towards? 0. That's my left hand end behavior right here. Right here, my right hand end behavior, as x goes towards what? Is that because it's going up? So it's going to the right. Remember, x is going right. So as x goes to infinity, what's y going towards?
Infinity.
Still going up.
Infinity.
And so remember, what happens to our features? They transpose. So this x is going to become a y, and this y is going to become an x. So this should be, as x goes towards 0, y goes towards negative infinity. See how I switched my x and y? Is that what we see right here? As x goes to 0, y goes to negative infinity? That's it.
I've been acting collaborating all day.
Uh-huh, you've been engaging.
I took my beats off.
I did. I saw that. I appreciate it.
Yeah.
So notice once again, my features just transpose, or my features switch, because what's happening with my inputs and outputs? They transpose. Okay? My features transpose, or my features switch. So, now we gotta look at the asymptotes. Am I gonna get my asymptote from the original function, from the left hand in behavior, or from the right hand?
Both.
You say both? I don't think it's both. Remember, asymptote, it's a what? Should have this definition down.
Oh,
It's a line or a curve that the function
approaches.
approaches at an infinity. So what is a line that the function approaches at an infinity?
Right.
The y, or the x-axis, which is y equals 0. We can see it right here. At this infinity, y is approaching 0. But what's it going to be for the inverse function? Look at your end behaviors. That's not the line it's approaching. Remember, it's approaching what line? The y-axis, which is where x is equal to 0, right? Remember how my inputs and outputs transpose?
Yup.
So what was a y is now an x,
Yup.
right? That
P.
is the line that the function is approaching.
I understand it.
X equals 0. Good.
I'm feeling myself.
Okay.
I ain't got no quadratic.
What are your questions? Okay. Go for it. Say again. Remember, it's a line that the function approaches. See how this function approaches the y-axis? So at the y-axis, x is equal to 0. You see how x approaches 0 as y goes to negative infinity? This is the infinity. This is the line that the function approaches. Right?
Can you only do that for exponential?
And there's actually something called a rational function that we're not studying that also has it. But logarithms and exponentials have asymptotes. Okay. All right. I need to take just a couple minutes to just point this out. It's on the very next page. Logarithms are what again? What does it say? Exponents, right? So I need you to pay attention to this. If I have 4 squared, what does that equal?
16.
16. So then the square root of what is equal to what? Based on this statement.
16.
Square root of 16 is equal to 4, right? 4 cubed is equal to, I'm going to go ahead and tell you, 64. So based on that information, which root am I going to deal with? Well, the cube root of 64 is equal to
4.
Notice what was the input has become the output. What was the output has become my input. And the power and the index are the same. So now, if I were to tell you 2 to the third is equal to 8, remember a logarithm is the inverse of a what?
Exponential.
Alright, come on now.
My fault.
So, with this, right, what I'm going to do is I'm going to take log base 2 of 8. What was my output is becoming my input. And what is a logarithm? It is an, so the input of 3 has now become my output. So a logarithm is just an exponent. So, we'll do some more of this tomorrow. Yeah, make sure you understand what a logarithm is. So, okay, you're looking at this one. A logarithm is an exponent, right? So what exponent goes on 5? Not 5 to the 5th. Isn't 5 squared equal to 55? So you see how the bases are the same. This output was the input, right? And this output is this input. Well, it's an inverse, right? So they are transposed, right? So a logarithm is the inverse of an exponential. But we'll get some more practice with that tomorrow. Just update. No, I was looking for details on where you're getting this. Yeah, that's all it is. That was it. Yep. I think overall you did pretty well on that demonstrate your understanding.
Yeah, I think it is.
What'd you do for